Hello and welcome everyone to Sciencera. In this video, we are going to look at carboxylic acid derivatives from organic chemistry CHE1502 module. I will be using LG Wade 7th edition to cover this module. Let's begin. Carboxylic acid derivatives. Carboxylic acid derivatives are defined as compounds with functional group that can be converted to carboxylic acid by a simple acidic or basic hydrolysis. The most important acid derivatives are esters, amides, and nitriles. Acid halides and anhydrides are also included in this group, although we often think of them as activated form of the parent acid rather than completely different compounds. Like amides, esters are common both in nature and in chemical industry. Animal fats and vegetable oils are mixture of ester, as are waxy materials such as beeswax and spermaceti. Plants often synthesize esters that give characteristics, taste, and odor to the fruit and flowers. Some naturally occurring esters and amides are shown here. Isoamyl acetate gives ripe banana their characteristic odor, and geranyl acetate is found in the oil of roses, geranium, and many other flowers. N,N-diethyl metatolamide, also known as DEET, is one of the best insect repellent known, and penicillin G is one of the antibiotic that has revolutionized modern medicine. Structure and nomenclature of acid derivatives. First we have is esters of carboxylic acid. Esters are carboxylic acid derivative in which hydroxy group is replaced by an alkoxy group. An ester is a combination of carboxylic acid and an alcohol with loss of molecule of water. Ester can be formed by Fischer esterification of an acid with an alcohol. Esters are named as alkyl carboxylates. The first word is derived from alkyl group of the alcohol and the second word from the carboxylate group of the carboxylic acid. Ester reaction of OH and carboxylate on same molecule produces a cyclic ester called lactone. To name, add the word lactone to the iupac acid name or replace the iic acid of the common name with O-lactone. Methyl 2-phenyl ethanoate or methyl phenyl acetate and ethyl ethanoate, also known as ethyl acetate, is an example of esters of carboxylic acid. Examples of lactones include 4-hydroxybutanoic acid, also known as hydroxybutyric acid or butyrolactone. Next we have is amide. An amide is a composite of a carboxylic acid and ammonia or an amine. An acid reacts with an amine to form an ammonium carboxylate salt. When this salt is heated to well above 100 degrees Celsius, water is driven off and an amide is formed. The simple amide structures shows a non-bonding pair of electron on nitrogen atom unlike amines. However, amides are only weakly basic and we consider the amide functional group to be neutral. A concentrated strong acid is required to protonate an amide, and protonation occurs on the carbonyl oxygen atom rather than on the nitrogen. This lack of basicity can be explained by picturing the amide as resonance hybrid of the conventional structure and a structure with a double bond between carbon and nitrogen. This resonance representation correctly predicts a planar amide nitrogen atom, that is sp2 hybridized to allow pi bonding with carbonyl carbon atom. For example, formamide has a planar structure like alkene. The carbon-nitrogen bond has partial double bond character with a rotational barrier of 75 kilojoules per mole. Classes of amide. Amide can be divided into three classes: primary, secondary, and tertiary. First degree amide or primary amide has one carbon-nitrogen bond or two nitrogen-hydrogen bonds. Second degree amide or secondary amide, also known as N-substituted amide, has two carbon-nitrogen bond or one nitrogen-hydrogen bond. Third degree amide or tertiary amide, also known as NN di-substituted amide, has three carbon-nitrogen bond and they don't have nitrogen-hydrogen bond. Example of first degree amide is propionamide, second degree amide is N-methyl acetamide, and tertiary amide example is dimethyl furamamide. Nomenclature of amide. First degree amide, also known as primary amide. To name a primary amide, first name the corresponding acid, drop the iic acid or oic acid suffix and add the suffix amide. For secondary and tertiary amide, treat the alkyl group on nitrogen as substituent and specify their position by their prefix N. Amides are named by using the suffix carboxamide for alkane carboxylic acid. Cyclic amides are also called lactam. To name cyclic amides, add the word lactam to the iupac acid name or replace the iic acid of the common name with O-lactam. Nitriles. Nitriles contain cyano group. Both the carbon atom and the nitrogen atom of cyano groups are sp hybridized and the bond angle is 180° or linear. The structure of nitrile is similar to that of a terminal alkyne, except that the nitrogen atom of the nitrile has a lone pair of electrons in the place of acetylenic hydrogen of alkyne. Although nitriles lack the carbonyl group of carboxylic acid, they are classified as acid derivatives because they hydrolyze to give carboxylic acids and can be synthesized by dehydration of amide. Nomenclature of nitriles. Common name of nitriles are derived from the corresponding carboxylic acid. Begin with the common name of acid and replace the suffix iic acid with the suffix onitrile. The IUPAC name is constructed from the alkane name with suffix nitrile added. For the acids that are named as alkane carboxylic acid, the corresponding nitriles are named by using the suffix carbonitrile. For example of carbonitrile is cyclopropane carbonitrile. Acid halides, also known as acyl halides. These are more reactive than carboxylic acid, so they are used to synthesize other acid derivatives such as esters and amides. They are used in Friedel Crafts acylation to make acyl benzenes. The halogen atom of an acyl halide inductively withdraws electron density from the carbonyl carbon, enhancing its electrophilic nature and making acyl halide particularly reactive toward nucleophilic acyl substitution. The halide ion also serves as a good leaving group. Nomenclature of acid halide. An acid halide is named by replacing the iic acid suffix of the acid name, either the common name or IUPAC name, with -ile and halide name. For acids that are named as alkane carboxylic acid, the acid chloride are named by using the suffix carbonyl chloride. Some example of acid halides are ethanoyl fluoride, also known as acetyl fluoride, propionyl chloride or propanoyl chloride, 3-bromobutanoyl bromide, and cyclopentane carbonyl chloride. Acid anhydrides. The word anhydride means without water. An acid anhydride contains two molecules of an acid with the loss of molecule of water. Addition of water to an anhydride regenerates two molecules of carboxylic acid. Anhydrides are more reactive than acids but less reactive than acid chloride. A carboxylate ion is the leaving group in nucleophilic acyl substitution reaction. Example of an acid anhydride include trifluoroacetic anhydride and acetic formic anhydride. Nomenclature. The word acid is replaced with anhydride. For a mixed anhydride, name both acids. Nomenclatures of multifunctional compound. With all different functional groups we have studied, it is not always obvious which functional group of multifunctional compound is the main one and which group should be named as substituent. In choosing the principal group for the root name, we use the following priorities. Acid is greater in priority than ester, followed by amide, nitriles, aldehyde, ketone, alcohol, amine, and alkene or alkyne. The table summarizes the priority in order and together with the suffix used for the main groups and prefix used for the substituent. For example, carboxylic acid. The main group of carboxylic acid is oic acid and the name of substituent used is carboxy. Ester, the main group name is O8 and the substituent is alkoxycarbonyl, followed by amide. Name of the substituent is amido. For nitriles, main group is nitrile and substituent name is cyano and so on. Physical properties of carboxylic acid derivatives. The physical properties of acid derivatives depend largely on their polarity and their hydrogen bonding properties. The graph shows the boiling points of simple acid derivatives plotted against their molecular weights. The N-alkanes are included for comparisons. Notice that ester and acid chloride have boiling points near those of unbranched alkane with similar molecular weight. These acid derivatives contain highly polar carbonyl group, but the polarity of the carbonyl group has only a small effect on the boiling point. Carboxylic acids are strongly hydrogen bonded in the liquid phase, resulting in elevated boiling point. The stable hydrogen bonded dimer has a higher effective molecular weight and boils at a higher temperature. Nitriles also have a higher boiling point than esters and acid chloride of a similar molecular weight. This effect results from a strong dipolar dissociation between adjacent cyano groups. Amides have surprisingly high boiling point and melting points compared with other compounds of similar molecular weight. Primary and secondary amide participate in strong hydrogen bonding. Pure tertiary amide lack nitrogen-hydrogen bond as we discussed earlier, so they cannot participate in hydrogen bonding, although they are good hydrogen bond acceptor. But still they have high boiling point, close to those of carboxylic acid of similar molecular weight. Melting points. Amide have very high boiling points and melting points compared to other compounds of similar weight. Melting points increase with increasing number of nitrogen-hydrogen bond. Tertiary amide cannot form hydrogen bond but still have high boiling point. Solubility. Acid derivatives, ester, acid chloride, anhydride, nitriles, and amides are soluble in common organic solvent such as alcohol, ether, chlorinated alkane, and aromatic hydrocarbons. Acid chloride and anhydride cannot be used in a nucleophilic solvent such as water and alcohol. However, because they react with these solvents, many of the smaller ester amides and nitriles are relatively soluble in water because of their high polarity and their ability to form hydrogen bonds with water. They are known to be a good polar aprotic solvents. Ethyl acetate, as shown in graph, is a moderately polar solvent with a boiling point of 77 degrees Celsius, convenient for easy evaporation from a reaction mixture. Acetonitrile dimethylfuramide or DMF and dimethylacetamide DMA are highly polar solvents that solvate iron almost as well as water. But without the reactivity of OH and NH group, these three solvents are miscible with water and are often used in solvent mixture with water. Reaction of carboxylic acid derivatives. Interconversion of acid derivatives occurs by nucleophilic acyl substitution. Nucleophile adds to carbonyl forming a tetrahedral intermediate. Then elimination of the leaving group regenerates the carbonyl. Nucleophilic acyl substitution are also called acyl transfer reaction because they transfer the group to attacking nucleophile, acyl group to the attacking nucleophile. Addition-elimination mechanism of nucleophile acyl substitution. Addition-elimination mechanism includes two steps. In first step, addition of nucleophile gives a tetrahedral intermediate, and in next step, elimination of the leaving group regenerates the carbonyl group. Reactivity of acid derivatives. The reactivity of acid derivatives towards nucleophile attack depend on their structure and on the nature of attacking nucleophile. Carboxylate is less reactive but more basic as compared to acid chloride, which is more reactive but leaving group is less basic. Interconversion of derivatives. In general, we can easily accomplish nucleophilic acyl substitution that converts more reactive derivatives to less reactive ones. Thus, an acid chloride is easily converted to an anhydride, ester, or amide. An anhydride is easily converted to an ester or an amide. An ester is easily converted to an amide, but an amide can be hydrolyzed only to the acid or carboxylate ion in basic condition. The figure graphically summarizes the conversion. Notice that thiol chloride SOCl2 converts an acid to its most reactive derivative, the acid chloride. Conversion of an acid chloride to an anhydride. Acid chlorides are most reactive acid derivatives, so they are easily converted to any other acid derivative. Acid chlorides are often used to synthesize anhydrides, esters, and amide. Acid chloride react with carboxylic acid or their carboxylate salt to form anhydride. Either oxygen atom of an acid can attack the strongly electrophilic carbonyl group of an acid chloride to form a tetrahedral intermediate. Loss of chloride ion and a proton gives an anhydride. The example of conversion of acid chloride to an anhydride include heptanoyl chloride reacts with heptonic acid to give you heptanoic anhydride. Conversion of an acid chloride to an ester. Acid chloride reacts rapidly with alcohol to give ester in strongly exothermic reaction. This reaction requires caution to keep temperature low to avoid dehydration of alcohol because acid chlorides are powerful dehydrating agents. Pyridine or another base is often added to the solution to neutralize the HCl byproduct. This is another reaction that follows the standard addition-elimination mechanism, ending with the loss of proton to give the final product. Example of conversion of an acid chloride to an ester include cyclopentane. Cyclopentane carbonyl chloride will react with propane 2-ol to give 2-propyl cyclopentane carboxylate. Conversion of an acid chloride to an amide. Acid chloride react rapidly with ammonia and amine to give amides. The HCl generated by the reaction can protonate the amine starting material, so a two-fold excess of amine is required. Alternatively, a base such as pyridine or NaOH may be added with amine to neutralize the HCl and avoid having to use the large excess of amine. Hexanoyl chloride reacts with primary amine, cyclohexylamine, to give secondary amide, N-cyclohexyl hexanamide. Conversion of an acid anhydride to an ester. Acid anhydride are not as reactive as acid chlorides, but they are still activated towards nucleophilic acyl substitution. An anhydride react with alcohol to form an ester. For example, cyclopentanol reacts with acidic anhydride to give cyclopentyl acetate and acetic acid. Conversion of an acid anhydride to an amide. Anhydrides react quickly with ammonia or amine. Reaction of an anhydride with ammonia gives primary amide. And anhydrides react with the primary amine to give a secondary amide and with secondary amide to give a tertiary amide. For example, aniline reacts with acetic anhydride to form acetanilide with acetic acid. Conversion of an ester to an amide. Esters are less reactive than anhydride, but they can be converted to amide by heating with ammonia or an amine. This reaction is called ammonolysis, meaning lysis means cleavage of an amine. Ammonolysis using ammonia gives primary amide. Primary amide react to give secondary amide, but secondary amines react often slowly to give tertiary amide. In each case, the acyl group of ester is transferred from the oxygen atom of alcohol to the nitrogen atom of the amine. For example, ethyl formates react with cyclohexylamine to give N-cyclohexylforamide with ethanol. Loss of an alkoxide ion as a leaving group in the second step of ammonolysis of an ester should surprise you. In our study of alkyl substitution and elimination reactions such as SN1, SN2, E1 or E2, we saw that strong bases such as hydroxide and alkoxide are poor leaving groups for these reactions. If we compare the acyl addition-elimination mechanism with SN2 mechanism, the difference in the mechanism explains why strong bases may serve as the leaving group in acyl substitution even though they cannot in alkyl substitution. The figure shows the comparison of SN2 and acyl addition-elimination reaction with methoxide as the leaving group. In the concentrated SN2, methoxide leaves in a slightly endothermic step and the bond to methoxide is largely broken in transition state. In the acyl substitution, methoxide leaves in an exothermic second step with a reactant-like transition state. The bond to the methoxide has just begun to break in the transition state. Nucleophilic acyl substitution is our first example of a reaction with strong bases as a leaving group. We will see many additional examples of such reaction. In general, a strong base may serve as leaving group if it leaves in a highly exothermic step, usually converting an unstable negatively charged intermediate to a stable molecule. This brings us to the end of carboxylic acid derivative chapter. Thank you for watching. If you like my video, don't forget to subscribe.